So in today's video, it's going to be a little bit of a longer format. We're going to discuss networking. We're going to discuss IP addressing, switching, routing, hubs, OSI models, all sorts of this fun stuff and how it all kind of fits together. This is the basic networking that everybody needs to understand, not only just to work with cloud technologies, whatever cloud platform you want to use, but also to work with on-site technologies, and in addition to that, things like Docker and Kubernetes. If you don't know your networking, most of what you're doing in IT is not going to make much sense. So hopefully this will give you a great overview of how this all really works under the hood and gives you a much better understanding of how networking actually works. So let's get on with it. Morning everybody. Today we're going to be discussing networking. We're going to discuss all those little things about networking that everybody should know. Whether you're working in cloud engineering, whether you're working with Cisco kit, whether you're working with your just home network or with Docker containers or absolutely anything. These are all the basic bits of networking you really need to know to further your career in IT. This is probably a large component of, say, a CompTIA Network Plus, but it will be relevant to everything you're doing. So the things I want to actually cover in this long format section, I'm going to cover cat cables, IP addresses. We're going to discover the different types of cat cables we've got out there. We're going to discuss private IP addresses, public IP addresses. We might discuss the differences between IPv4 and IPv6. We'll discuss how MAC addresses hook in with IP addresses and how they connect to each other to then be able to route traffic through switches and hubs. We're going to discuss routers and routing tables, how our packets of data get maneuvered between different networks and across the internet. We're going to discuss subnets and CIDR notation. This is also going to lead us into talking about how to do decimal to binary conversion, because we're going to need to do that to understand what that is. We're then going to discuss the final OSI model, the 7-layer OSI model here, to understand how packets of data are actually put together and are routed across our networks. We do need to know kind of all of this really for our networking to actually be understood. Whether you're doing, as I say, things in Azure, things in AWS, things in GCP, or even doing stuff on site, all of this is going to be relevant. So let's start off. With talking about cat cables over here and actually basic units of network cable. Now there are a number of different types of network cables that exist out in the world, including fiber cabling, but most of our networking today is still run with cat cabling, and cat cabling kind of looks a bit like this. If I pull over here, you've seen these around the office, you've seen these at home. These are standard cat cables. You probably call these Ethernet cables, even though Ethernet is actually technically the protocol that runs inside here. These are called cat cables, which is short for category. Okay, and this table down here are your different types of cat cables. Now each of these cat cables from Cat5e through to Cat7a, they all look exactly the same. You couldn't tell the difference between a Cat5 cable or a Cat7a cable without actually going to look at it. If you look very, very closely here on these cables, there is writing on the cables, and normally what is printed on there is actually the category of cable. These cables are also known as something called twisted pair. The reason they're called twisted pair cables is, well, because inside these cables what we've actually got is 8 individual sets of cables here, and these are twisted into 4 different pairs. Now even though there's 8 cables inside here, technically only 4 of those 8 cables, as you can see here, are used for traffic. The other 4 cables in here are actually twisted and combined with these traffic cables, so you kind of get like this little helix approach inside the cat system. Inside the cat cable itself. The reason is if you've got a live cable and you've got a neutral cable and those are twisted between each other, then those cables will be able to transmit a cleaner signal. Essentially it shields it There is also STP cable as well, and UTP cable, something called shielded twisted pair and unshielded twisted pair. Shielded twisted pair cable or unshielded twisted pair cable, you can't tell the difference between these two. You can't tell the difference between them just by looking at them, but inside this cable here, what you've actually got is an aluminium sheath that goes around it, and that will provide some shielding against electromagnetic interference. Unshielded twisted pair is the cheaper format and the one that's normally used on a day-to-day basis. Now, inside these cables, dependent on the quality of the copper and dependent on how many twisted pairs you've actually got in the cable, it goes up this category format. And as we go up from Cat 5 up to Cat 7, we get the ability to essentially send more traffic through it. So for example, Cat 7 and Cat 7A down here, and Cat 6 and Cat 6A, these guys actually have the ability to transmit up to 10 gig Ethernet down here. Okay. You could try and jam 10 gig Ethernet across Cat 5, but you might not actually get up to 10 gig Ethernet going through here, or 10 gigabits worth of connection. It's still the same amount of cables, so still connect. The only difference is essentially the quality of the cabling inside there. Now the connectors that are connected to the front end of one of these things, these little connectors, these are known as RJ45 connectors for the most part. The Cat 7s and Cat 7As have slightly different connectors. They have Terra connectors down here, which is shielded. But most of the things you're going to see today are still RJ45 cables and look like this. They actually have a pin out guide. So inside this cabling, you actually have these 8 cables, which are all colored in this exact same way. So we've got orange, white, orange, orange, green, white, blue, blue, white, green, brown, white, brown. So normally what you actually get is you get these cablings here come in really, really long reels, like 300-400 meters. And what you will do is you'll cut them to the sizes you actually need, and then you will add one of these RJ45 connectors on the end with a tool called a crimper. Okay, and a crimper looks like, if we can just bring this up here, RJ45 crimper. A crimper tool looks a little bit like this. So if I just take that tool here and copy that image and paste that in here as well, just to add it to the collection of stuff we want to talk about. So this crimper up here is going to have a number of components to it. One of those components is for cutting the cable. The other one is where you would put a plastic RJ45 connector in it, and then you would actually thread the cabling through that RJ45 connector and press it down. If you look at an RJ45 connector in detail, so if you look at RJ45 connector in detail, you'll notice there's a couple of things attached to it. Here there are these little raised pins, and here we've actually got these little teeth. And what happens is when you go to crimp one of these devices, those teeth actually get pushed through these tiny little wires, breaking the seal on the outside of those wires and touching the inside of the copper. Now, this is actually something that has been around for a lot longer than Cat cabling. Back in the 90s, there used to be these things called vampire taps. Oops. There we go. Oh, that'll do. These things called vampire taps. And these were used for really old coaxial cabling. So this was one long strip of copper. And a vampire tap would actually have a couple of teeth that would come down and insert through that cabling and touch that copper cabling inside it. Vampire taps. Looked a bit like that. They're completely irrelevant now. We won't see those at all. So these little things here, these Cat cabling and these RJ45 pins, are going to plug into one of these kind of devices on the basic level. Now these are either going to be hubs or switches. You can't tell the difference between a hub or a switch just by looking at it. It's not really possible unless you actually read what's on the box itself. So what's the difference between the two? Well, the general idea is that hubs are dumb and switches are smart, sort of. We'll get into a little bit more detail with these later on. when we start to discuss things like the OSI model and how packets are actually created. Generally today in 2023, we won't actually really see hubs anymore. We will really only see switches, but it was common for a period of time to see both of them at once and to know the difference between a hub and a switch. So let's reverse out of here. After we plug devices in, we need to start talking about IP addresses, and we need to start talking about how computers actually communicate to each other here. So let's neaten that up a little bit. Let's drop down and let's start to draw some form of diagram out here. So we have a computer, and we have maybe another computer over here, and these two computers want to talk to each other. Now these two computers are going to have inside them some form of NIC, some form of network interface connector. Okay, and that NIC could be a Wi-Fi card, but for the moment this is just going to actually be a physical network card attached to the computer. So something like this. We go and look for a network card, some form of physical network card sticking in the back of your machine. Now, most laptops and desktops today have these integrated, but that's what one kind of looks like if you connect it to PCI Express in your computer. Some of these actually come with multiple RJ45 ports attached to them, but the basic ones will just come with a single RJ45 port. Now, what's interesting about these network cards is a physical address of the network card itself. Now, these NICs are going to have installed into them something called a MAC address. Okay, so both of these guys are going to have a specific MAC address. Now a MAC address is also what's known as a hardware address. Now this hardware address used to actually be pretty static. Today we can change it, we can do something called spoofing with it. But if we go and have a look at my computer here, and we go and run ipconfig /all on this machine, you will see quite a lot of information down here. But what you will also see here is my Ethernet connection. Okay, this is my network card that's attached to my computer at the moment, and you'll notice it has this physical address, something like 00D861 and so on and so forth. If I just copy and paste that in here, that's what a MAC address is actually going to look like on one of these network cards. If I copy paste that again, just drop it over here, we're going to change this MAC address so it's actually unique. We'll call it BB on the end. Now, these MAC addresses are split. In fact, they're split down the middle here. Generally, what's actually going on is at this side, you've actually got the manufacturer. I can't really spell. Now, the manufacturer is going to be somebody like Cisco, Juniper, Realtek, whoever actually that might be. And these guys actually apply for specific ranges that they can use. Now, some really cheap Chinese ones coming out of strange places in Guangzhou might be a little bit wonky. But the general idea is that since these are all centralized and assigned by IANA, the Internet Assigned Names Authority, these aren't going to cross over. This second section here is unique. Okay, it's unique to that specific network card out of all the other network cards in the world. So let's just drop back on this a little bit. Now these unique addresses are great because now we can actually start to plug these into things. So we could have in the center of all this, we could have something like a switch or a hub. And this will allow us to physically connect with our CAT cabling these multiple computers together. But they're not going to be able to communicate with each other just yet. These multiple computers need something else on top of them. Sure, the MAC addresses are the actual physical addresses of the network cards, but we still need something else laid on top of this. We need something called IP addresses. Okay. Now, IP or Internet Protocol addresses, This is part of something called the TCP/IP stack. Now, there was actually multiple ways of computers talking to each other a number of years ago, especially in the 90s. There was things like Apple Talk, and there was things like IPX, SPX. These are things that really don't exist anymore, and don't need to exist anymore, because they weren't really compatible with what we consider today as the modern day internet. Now, our IP addresses for these computers, we have a number of spaces with them. So let's discuss IP addresses and then we'll come back to this diagram. Okay. So within IP addresses, an IP address is actually split up into what's known as 3 octets. Okay. So you may have seen an IP address like this, like 10.10.10.10. In fact, if we look at my computer down here, my IP address down here is 192.168.178.65. Okay. Now, each of these IP addresses can technically go up to 255, 255, 255, 255, sort of. Okay. In fact, the reason why we can go 255, 255, 255, 255 here, and why each of these sections here are called an octet, is because of binary. Okay, so we need to learn how to kind of convert some decimal into binary. As we know, binary is just ones and zeros, and what that means is this is actually something called a base 2 numbering system. Your standard numbering system that you use every day, 0 through to 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, that's actually known as a base 10 numbering system because we've got 10 numbers to use. So binary is base 2 because we're just using numbers 1 and 0. Now, if we take IP addresses, these things like 10.10.10.10 and 255.255.255, and any other IP addresses which we'll discuss in more detail in a moment, and we convert them to binary, what you'll actually find is that each of these individual sections here can support up to 8 binary bits. So let's just do a quick conversion here. Let's do a bit of binary to decimal conversions. So let's take some common sort of numbers here. Let's take the number of 10 and let's take the number of 99 and let's take the number of 150 and let's take a final number of 255. And what I want to do is I want to convert these decimal numbers here on this side, these decimal numbers, and I want to convert them into binary. Now, to do that, we don't need to know how to convert massive numbers into binary. But what we do know, we need to know from a networking level, is how to convert up to the number of 255. Well, technically it's 256, but we count 0. So to do this, what we're going to need to do is we're going to need to create a table. Okay, and we're going to need to create a doubling table down here. So what we're going to do is we're going to start with a table that goes 128, 64, 32, 16, 8, 4, 2, 1. Okay, and with this table we're now going to start converting things, and it's very, very easy to convert decimal to binary. Watch this. All we need to do is make some comparisons. So if we take this decimal of 10, what we need to do is work through each column. Does 128 go into 10? No, it doesn't. Does 64 go into 10? No, it doesn't. Does 32 go into 10? No, it doesn't. Does 16 go into 10? No, it doesn't. Does 8 go into 10? Yes, it does. Okay, so now if we do 10 minus 8, what do we get remaining? We get 2. Does 4 go into 2? No. Does 2 go into 2? Yes. And what do we end up with? 2 minus 2. We end up with 0. There's nothing left to do. So 10 in binary is actually 1010. Okay, we can ignore these leading zeros over here. So let's do that again. Let's do the next one down. Let's do 99. Does 128 go into 99? No. Does 64 go into 99? Yes. Okay, so let's just do 99 negative 64, which will be brain. 99, negative 64, 35. I think I need more coffee here. So that goes once into there. Does 32 go into 35? Yes, it does. It gives us a remainder of 3. 16 go into 3? No. 8 go into 3? No. 4 go into 3? No. 2 go into 3? Yes. Negative 2 gives us a 1. Does 1 go into 1? Yes. So 99 in binary is 0. Well, we don't technically need that 0. It's 1, 1, 0, 0, 0, 1, 1. Awesome. Let's clean this up a little bit. And let's do another one. Let's do 150. So 150, does 128 go into 150? Yes, it does, once. Okay, so we do 150 minus 128, which is equal to 22. Yep, 22. Does 64 go into 22? No. Does 32 go into 22? Does 16 go into 22? Yes. Minus 16, that gives us 6 on the remainder. Does 8 go into 6? No. Does 4 go into 6? Yes. That gives us 2 on the remainder. Does 2 go into 2? Yes. And therefore, we've got a 0. Now, the final piece of the puzzle down here is 255. What happens if we do this? Well, if we go 1, 2, 3, 4, 5, 6, 7, 8, what do we get? We get our 255, or our 255 in here. So, how many of these binary bits have we got? 8 binary bits. Since we have 8 binary bits, they are called an octet. So if we convert something like 10.10.10.10 and we convert that to binary, remember 10 is 00001010. So let's go for 00001010 dot 0000 dot 001010 dot 2341010 dot 123411010, and that is the same as that. Now, with these IP addresses, there's also a couple of different main types of IP addresses. All right. Now, if you'd like to do a bit of binary to decimal conversion there, and that table, relatively simple when you know how. Let's come back up here and let's talk about the different types of IP addresses we might actually have. More to the point, we're going to talk about the fact that we have something known as public IP addresses and we have something known as private IP addresses. Now, public IP addresses, these are IP addresses that work on the internet. Okay? These are IP addresses that can be routed across the planet, across the internet to different computers around the place. Private addresses, on the other hand, these addresses can only actually work internally. Well, they're also known as internal addresses. Anybody can use these addresses, but you can't communicate to them over the internet. We have to go through a bit of translation to be able to actually get to those IP addresses. These are defined in something called RFC 1918. You can go and Google that if you really want to. In reality, it's basically this table over here. These are the private address classes. Now, there is actually a couple more listed in here too. In fact, what's missing here is we're also missing something called loopback, which is anything inside the 127 range. And we're also missing something called APIPA, the APIPA range, which is 169.254.something.something, and we'll come back to those later on. But in reality, there is these three classes: Class A, Class B, and Class C addresses. So Class A addresses is anything with 10, or starting at 10. Class B is anything starting with 172.16 up to 172.31. And Class C is anything starting with 192.168. Now, each of these has something on the back end of it called a CIDR prefix. This is also sometimes called a CIDR prefix or CIDR notation. Now, when you're looking at a collection of IP addresses, what we are looking at is we're looking at subnets of IP addresses. We'll get through to those in a moment. What I want to do now is I want to come back to our original diagram, and then we'll reverse back into these private addresses in a moment. So let's drop back into our switches down here, okay, and back into our computers. Now our computers might not actually have, our computers will have MAC addresses, but what they will also have on top of them is they will also have on top of them IP addresses. So for example, this guy might be called 10.0.0.10, and this guy might be called 10.0.0.20. Okay. Now there's something else inside here. We also need something called a subnet mask. Okay. Because these two computers, to be able to talk to each other, actually need to be in something called the same subnet. So what is a subnet mask? A subnet mask. A subnet mask defines what is a host portion and what is a network portion of an IP address. So if we come over here, let's get a little bit more space down here, and we take an IP address like 10.0.0.10, okay? If we have multiple computers that are talking to each other within the same network, they all need to be on the same subnet. Essentially, they all need to have the same network portion of this IP address. So whenever you see an IP address, you will also see it come with a subnet mask. 255.0.0.0. Generally with class A addresses, this is what the subnet mask looks like, 255.0.0.0. And what that's doing is it's essentially drawing a line here. It's drawing a line between something called the network portion and the host portion. Think about it a little bit like towns and cities, in the sense that everybody in London would have a London postcode, or if you're in America, everybody in New York would have a New York-based zip code. Whereas they would also have a unique component at the end of that, which would allow them to be a little bit more localized. So here, within the network portion, every computer that is within this subnet actually starts with this same network portion and has a unique host portion. What this actually does is, if you take these 3 octets here, it gives us uniqueness. We can have up to 16 million addresses. It's actually a much more specific number than that, but you can have 16 million unique computers within this single network. This is what will be known as a class A subnet. Now if you go a little bit further and you do something like 172.16.0.0 with a subnet mask of 255.255.0.0, the split is going to be here between the network portion and the host portion, so it moves along a little bit more. Since we actually have now 2 octets to work with, remember an octet is binary bits, we have a sum total of 16 binary bits to work with, which actually gives us the ability for 65,535 unique addresses. This is our class B. Our class C is actually moving that up a little bit more again. So you'll notice this actually representing the same situation over here. Now, technically, the RFC standards underneath, especially within class B, is actually from 172.16 up to 172.31. Most of us tend to really just use 172.16 down here. Generally, the 3 ranges that people tend to use commonly is the 10 range, the 172.16 range, and the 192.168 range. Instead of using these side of prefix notations here of 8, 12, and 16, what we actually tend to use more is /8, /16, /24. So, what does this mean? Let's come back across again. So more commonly, if you see class C addresses, the most common kind of class C addresses is 192.168.0.0 with a subnet mask of 255.255.255.0. and we can put a slash in between here. This gives us only 8 binary bits to actually work with, and we can't use 255, so technically this gives us 254 hosts that we could have within that specific network. Now, the idea with that thing called CIDR, or classless inter-domain routing, is that when you look at IP addresses and you look at this kind of stuff here, and we see, for example, I have my IP address and my subnet mask of 255.255.255.0, but I have an IP address of 172.168.65. My network portion of my environment here is 172.161.78. Now, if I wanted to represent that differently, instead of having to draw out and say, hey, my IP address is 192.168.178.65 with a subnet mask of 255.255.255.0, I could just count these binary bits here. So I have 3 octets. I have 8, 8, 8, which gives me a total of 24 binary bits. So if you wanted to write this address as CIDR notation, you could do 192.168.178.65/24. That's it. That's CIDR notation. Hey everybody, if you're enjoying this video, click the button down below, subscribe, button with the bell icon, that'd be great. Comment any suggestions you've got. Thanks very much. So sometimes people will want you to actually use CIDR notation, and if you're using Azure, most of the time, most of the interfaces are built by using CIDR notation. Sometimes people will actually want you to use these methods of inserting the IP address and the subnet mask, depending on how you're actually defining it. So if we go back and have a look at our environment here, maybe we've got a computer A and we've got a computer B over here, and these two want to send a packet of information between each other, right? So how does that actually work? Well, technically they're not sending packets of data between each other via IP addresses. They're kind of working on MAC addresses, all right? But computer A does not know the MAC address for computer B. So how does this actually work? Well, we need another protocol involved in here for this to actually function. We need a protocol called ARP, or Address Resolution Protocol. Now, the way this actually works is it works with the concept of something called broadcast addresses. So if we go back to switches, right, and we go back to talking about what these things actually do. So a switch is going to have a series of different ports attached to it. Let's go and have a look at the pictures of a switch. Where has it gone? Here we go. It's going to have a series of different ports attached to it. Now, the switch actually knows when you plug something into it, it actually knows what MAC address is actually on each specific port. So, for example, it knows what the MAC address of computer A is, it knows what the MAC address of computer B is, and it knows the MAC address of computer C. Because when you make that initial connection and plug the thing in, what actually happens is the switch asks for it. It says, hey, what's your MAC address? And the network card responds and says, hey, this is me. And the switch actually stores that information in a little cache. Now, depending on how expensive this switch is, you can kind of manipulate that. If this is actually a proper smart switch, but normal switches, actually known as layer 2 switches, you won't be able to do anything with this. It will actually only be stored inside the switching device itself. So let's go back over to my diagram and discuss what this ARP thing does, right? So this switch knows that this MAC address here is connected to this port here. This MAC address here is connected to this port here. Okay, that's fine. That's fine. But the problem is computer A does not know the MAC address of computer B. So it's got to go find it. And the way it does that is it does that by using the concept of something called a broadcast. Okay? Broadcast. Technically, it creates a packet of data and it says, look, I need to communicate with you, right? I need to find out your MAC address. I don't know your MAC address, but I know what IP address it is I want to communicate to. I mean, I'm going to address my packet of data here. It's an IP address of 10.0.0.20. But I don't know what MAC address I should actually send that to. So I'm going to send out initially something called a broadcast packet. What a broadcast packet is doing is a broadcast packet is destined for a very specific MAC address. It's destined for a MAC address of okay, all Fs. And basically, if you convert that from hexadecimal to binary, it's just all ones, right? And what that special broadcast packet does, when that thing is sent to the switch goes, okay, I'm going to send this packet out of every single port within the switch itself. Okay, not to a specific port that's got a specific computer. And essentially, what this broadcast packet has inside it is a question mark. And this question mark says, who has 10.0.0.20? So this broadcast packet comes out of this switch, ends up hitting this computer because it's going to every single computer, and says, hey, does anybody have 10.0.0.20? And this guy looks at this broadcast packet, this computer B, and responds and says, yes, I am 10.0.0.20, and this is my MAC address. So it responds all the way back to this original computer. Now, there's a lot of lines going on here, so let's get rid of some of these lines. So what's actually happened now is this computer has something called an ARP cache, okay, or an address resolution protocol cache. Basically, what it's now got is it's got information about this MAC address. This computer A over here actually now knows that this MAC address here, let's just rub some of those lines off, this MAC address here belongs to 10.0.0.20. We can see this on our local computers as well. If we throw up a command prompt here, if we just do ARP on our computer, there is an ARP command. We can do ARP-A, which is going to show all of our current ARP data. And we can see from my computer down here, for example, 192.168.178.1, it's got a physical address. That's the physical address of my router. These are also other things on my network that my computer is actually communicating to. So that's kind of cool. So it maintains a cache of these things so it doesn't have to ask every single time. Now, what this computer can actually finally do is it can take that address and it can attach that address to that packet of data. So now, if we come back out of here, we know, or this computer knows, that this 10.0.0.20 exists in the same network that it does. So it can now send this packet of data into the switch. And so that packet of data goes all the way up into the switch up here. The switch can see that that packet of data is addressed to 10.0.0.20, but the switch doesn't understand IP addresses, the switch only understands MAC addresses. It can also see the MAC address that it's destined for, and the switch knows that this MAC address exists on this port, therefore it can send that packet of data out to that computer, which finally receives it. Awesome. So when we're sending packets of data between different machines on the same network or on the same subnet, it's actually firing that data with IP addresses and MAC addresses, the physical addresses of those network cards. Now we need to kind of expand this process up a little bit. So let's skim over here and let's neaten up that diagram a little bit more. So we have a couple of computers, again 10.0.0.10 and 10.0.0.20. And maybe we have a situation where we have, again, a switch inside here. All right, and both of these are nicely connected to our switch, but we're going to add another layer of complexity to this. we're going to add something else called a router. And we'll actually see how a router works. So this router might be also connected to this switch. That's perfectly fine. What we might have over here is we might have other machines on different subnets. So for example, maybe we've got 192.168.0.10 over here, okay? And this is connected to a switch, and this switch is also connected to this router. Now what a router does is allows us to intercommunicate between different subnets. Remember, we have a subnet over here, maybe we have a side notation of /8, and maybe we have a subnet over here of /24. Now these two machines can't communicate with each other at all. If they're on different subnets, you have to go through a router to communicate between those different subnets. And the way this actually works is an extra setting on our computers. So if we look at, for example, here, we have computer A, computer B, and maybe we have computer C over here. Now each of these devices are going to have a number of different addresses attached to them. One of those addresses is actually going to be known as their gateway address. So their gateway / their router address. Okay. Some environments you'll see it called gateway, some environments you'll see it called router, but the same concept exists. Okay. So this is a gateway, this is a gateway, this is a gateway. Now the gateway addresses are going to be the addresses of the network cards attached to these routers. So the key thing about a router is a router has multiple NICs attached to it. And it's going to have multiple IP addresses in multiple different subnets. So this router, for example, might have an IP address here of 192.168.0.1 and also have another address of 10.0.0.1. Two different network cards, two different IP addresses, two completely different subnets, and it can transfer data between these two. Now, say this, for example, is network card X and this is network card Y. What the router also has is something called a routing table. Okay, and very simply it states this: it knows that network card X is actually connected to the subnet of 10.something.something.something/8, and network card Y is connected to the network of 192.168.0.something/24. Now, you've got attached to these individual network cards of computer A and computer B these gateways. Okay, so these guys have a gateway of 10.0.0.0.1, and this has a gateway of 192.168.0.1. So the way this kind of functions is this. Say, for example, if this computer down here, computer A, had a packet of data, and that packet of data was destined for computer C. So this packet of data is destined for 192.168.0.10. Now, the very first thing that this computer does is it looks at this address and says, hey, is this address in my subnet? So, I'm currently in subnet of 10. It's not. All right, that's fine. So I don't know where this computer is, but I know it's not in my local environment. How do I know where to send it? Well, it would actually look at something called a routing table. Now, the router has a routing table. The computer also has a routing table as well. The computer might have multiple network cards and therefore need to know which network card to send this packet of data out of. In this situation though, and in most situations, the individual client computer or server is not going to have multiple network cards. It's only going to have one network card that it's actually going to be sending that traffic out of. And if that network card is in a subnet that is different to where this packet is going, it doesn't know exactly what to do with it. So it sends it to its default gateway. So in this sense, this packet of data just goes up here. Computer A has no idea what's going on with computer C or where computer C is. It doesn't particularly matter. But it just sends it up to this router, sends it up to its default gateway. And the router says, okay, fine. Let me just check that packet of data. And let me have a look inside that packet of data. And it goes, okay, it's going to 192.168.0.10. Well, let's have a look at the first section of that, the 192.168.0 bit. There's something in my routing table that tells me that exists on this network card. So what my router does here is actually, initially, it sends out a broadcast. The same thing that we saw before. And that broadcast hits this switch and it says, hey, FFFFFFFF, has anybody got this IP address, 192.168.0.10? This guy over here responds and says, yes, I do have 192.168.0.10. Great, the router goes, thank you very much. I will, kind of hold on to that information. I will put that into my ARP cache, just for future reference. And what I will then do is I will forward on this traffic or forward on this packet of information out of that network card via that switch into that computer. Okay, that's cool. That's cool. There is another element going on here as well. What about if this wasn't going to 192.168.0.10? What about if B, for example, is sending a packet of data out to the internet? Maybe it's sending it to 8.8.8.8. This is a public IP address. This is an IP address that exists on the internet somewhere. And all the internet is a vast collection of routers and switches, millions and millions of routers and switches, all intercommunicating with each other. It's this base concept extrapolated and scaled up to a ridiculous level of complexity. But how does that work here? Well, let's clean this up a little bit more. So let's just drop some of this information here. Let's clean this back up a bit. Okay. So now, whoops, a bit too clean. This routing table, and if you want to see what a routing table looks like, you can come to your client computer and you can do root print on your machine, and there's what a routing table actually looks like. These on routers that exist on the internet are huge, massively complicated with tens of thousands of entries in them. But on our basic routing tables here, we have got a couple of lines of entries in here, network card X, network card Y. Well, there might also be another network card attached to this router. And this other network card attached to this router, maybe this is network card, let's do X, Y, and Z. Okay. Maybe this network card Z is actually attached out to the big WWW. Maybe this is an old modem. Maybe this is an actual WAN connection. Maybe this is a connection to your ISP, your actual fiber optic connections. You could define this as, in your router, essentially the default gateway entry. So the default gateway here is actually going to be network card of Z. And that might have an IP address like 81.37.99.27. This is going to be an IP address that is valid on the internet. So now, in the sense of what's going on here, if we have this packet of data from B, and this packet of data is now being passed up through the switch, passed into the default gateway, because it's not part of B's range, the router looks at it and says, hey, 8888, that's not in any of my entries here, so all I will do is I will send it out of my default gateway. And that networking router then sends that packet of data out to the internet, which will then be picked up by another router in the ISP, and another router, and another router, and another router, until it gets to its final destination. This process is repeated as many times as necessary to route that packet of data to its final destination. Each router inside that sequence only knowing enough information to get to the next router. This all looks relatively complicated, and to be honest, it is, but these concepts come up constantly throughout all networking inside, not just Azure or AWS or on-site, but absolutely everything that we see. So we've had a look at CAT cables, IP addresses, MAC addresses, switches and hubs. We've had a look at routers / gateways and routing tables. There's a bit of subnets and CIDR notation. We've done decimal to binary conversion. The final piece of the puzzle down here is something called the OSI model. Okay? Or more to the point, the 7-layer OSI model. I think we'll probably save IPv6 for a little later. The concepts with IPv6 in regards to routing are relatively the same, but they're kind of expanded on a lot. Let's go and have a look though at this OSI model. This is it. The OSI model essentially defines how a packet of data is put together. So remember, we have those two computers. Okay, we have a computer communicating to another computer, and it's assembling a packet of data, an envelope I keep drawing. Because think about this like a postal message. Okay, you write a postal message out to somebody, you fold that piece of paper up, you put it inside an envelope, you write the address on, and you put a stamp on it and put it in the post box. That process is standardized. You have to write the address in a certain way. You have to put enough postage on that envelope. You have to actually have, well, some form of envelope to put that piece of paper in. All of this is an assembly process. And then the person on the other side essentially does a disassembly as they open that packet of data, pull out the piece of paper, unfold it, and read your message inside there. And maybe that message also has a return address. That's what this 7-layer OSI model is essentially defining. Okay, how these packets of data are put together and who can actually read specific things on those packets of data. So at the bottom layer of the OSI model, in fact, let's go with the top layer first and work our way down. So if we're building a packet of data, the application might be something like email, right? And within email, services that are used for end-user applications like SMTP. What you're going to do is you're going to take your data, your actual text data inside your email, and that's actually going to be formatted in a specific way. So that's the application layer. So we know that if we're receiving SMTP data or SMTP formatted data, to give that to an email client once it finally hits the computer. Or if it's the email client in the computer that's creating the data, we're starting at the top of this list. As we work our way through this list, what we're actually going to do is maybe attach more information to this or even encrypt that information. We're then going to pass this down into things like PPTP connections, point-to-point connections between two hosts, and things like TCP and UDP layers. So we're going to say, hey, this packet of data is coming out as an email. We're formatting it correctly, we're putting our information inside it, and we're essentially getting all the way down to attaching IP addresses to this. Once we're attaching IP addresses, we're into the kind of the transport layer, and certain things can read those. So for example, routers would operate here on what's known as layer 3-4. So routers operating in layers 3-4, why? Because a router can read the IP addresses that are actually attached to a packet of data. You get down a little bit further, and that packet of data eventually ends up on the wire. It ends up hitting switches. So switches are actually operating here because this is the MAC address layer, the data link layer. And then once it comes out of the switch, it's on that CAT cable, and it's actually voltage. That's it, it's just a waveform. This is the physical data link layer, so it's actually looking like a waveform on the cable itself. Essentially, this waveform is now passed over to this other computer and it reassembles it. It goes back up that layer. So it's receiving this waveform, which can then be decoded into data link, decoded into network and transport layer, and all the way up until application layer, where this final computer could read the information and go, hey, this is some form of SMTP, this is some form of email traffic, I need to give this to my email client. So what do you really need to know on this? Well, do you need to remember the OSI model? Not really, you can Google it, that's what Google's for. But what you really need to know is when somebody says, for example, a layer 3-4 switch, okay? If If they say layer 3-4 switch, they're sometimes meaning what they call a smart switch. Now switches, as we just saw, operate on that data link layer. But if you actually have a layer 3-4 switch, what they're talking about is switches that can actually understand IP addressing inside there as well. If we say, for example, we have a layer 7 web application firewall. If you're dealing with a layer 7 firewall, a layer 7 web application firewall, it means it can work all the way up to here, and it can look inside the packets of data as they flow across that firewall. So, for example, if you're attempting to filter traffic from a security perspective, you might not just be looking at dropping traffic from a specific IP address or a specific location. We might be looking at examining inside that packet of data. And when we look inside that packet of data, we might find out more information. So we might find out, for example, keywords we want to block, maybe things to do with things like gambling and bad language or whatever it might be. We might also want to extract information out of there to maybe look for bad commands like cross-site scripting that might be happening, or maybe SQL injection that actually might be happening with those packets of data. So yes, you don't necessarily need to remember the whole OSI model, but some of the terminologies, for example, layer 7 firewalls or layer 3-4 switches, are referencing this OSI model underneath, and by knowing what they do, you then know what the capability of those devices actually are. So let's rewind again. Whoops. And that crosses off that OSI model underneath here. So no longer is Vader finding your lack of basic networking protocols disturbing. You should hopefully now have a much better understanding of how TCP/IP works, how IP addresses work, how to do binary to decimal conversions, and all these fun things on top. If you enjoyed this series, please leave a comment below, and I'll do many more series on things like basic networking and hardware, things that actually are relevant to cloud computing, and things that are relevant to everything that we actually do within IT. I hope you enjoyed this longer format session, and remember, if you did, hashtag like and subscribe, and there will be more content in the future. Have a good day. And you know the routine, hashtag like and subscribe, and I hope you enjoyed this video and will join me next time. Goodbye.